Hello, good morning, everyone. The previous class we talked about basics of nucleus. We, we try to understand the mechanism of energy production using nuclear fission. We understood the difference between uncontrolled and controlled chain reaction. And then we talked about nuclear reactors and what is India doing in nuclear energy program. If you have any questions from the previous class, you can ask questions. Remove करते हैं? Anti-satellite debris create space debris. Even demonstration create debris. वो बहुत कुछ रेयर मिशंस हैं. द क्वेश्चन पहले तो एंटी सैटेलाइट डेमोन्स्ट्रेशन जो है दैट लीड्स टू क्रिएशन ऑफ डेब्रीज बिकॉज यू आर डिस्ट्रॉइंग अ सैटेलाइट. अब डिस्ट्रक्शन का मतलब ये तो नहीं होता है ना कि वो खत्म हो गया हो. वी कैनॉट डिस्ट्रॉय मैटर. हमने डिस्कस किया था. इट विल बी फ्रैगमेंटेड. स्मॉलर पीसेज में बढ़ जाएगा. इट विल बी फ्रैगमेंटेड. ऑल ऑफ दोज लिटिल फ्रैगमेंट्स विल बी डेब्रीज. So anti-satellite demonstration is in fact one of the source of space debris. There are some dedicated missions. What they're trying to do, they're trying to capture debris by deploying, let's say, things like space net. आप ऐसे समझ लो जैसे मछली को पकड़ते हैं fish में, pond में, right? So think of something like this, not exactly something like this, but a mechanism which can trap debris, and with the help of, let's say, laser beam, we aim to burn it in the space itself. Or if we can trap large, if we can capture large piece of debris and we try to then throw them towards lower atmosphere where they can burn up in the atmosphere. So, but all of these missions are quite expensive, and that is why you have like very few missions. I mentioned some of them. Yes. Not last stage, second stage. It will continue hundreds of years because we will be, so question is that why are we using thorium in the third stage? It will continue for hundreds of years because while we are producing energy, we will be simultaneously able to convert thorium into uranium, and the same uranium can be used in third stage itself. So the reason third stage will continue for hundreds of years, because in second stage we will not be able to exhaust all of the thorium. We have lot of thorium. We have lots and lots of thorium. So whatever thorium we will convert in fast breeder reactor to make uranium-233. Once you have enough, we enter into the third stage. And third stage is a proper closed loop nuclear fuel cycle. That you are using uranium, which you recovered from the second stage, to produce energy. But you still have lot of thorium left. Keep using that thorium for next 200, 300, 400 years and keep producing energy. Okay, now that's a valid question. Clearly, there were some design challenges. So the question is that why did we not start thorium in the very first stage itself? It must have something to do with the fact that spent fuel reprocessing in itself is very difficult. Creating a blanket of uranium, then thorium, while uranium-238 in itself is fertile. So why we did not use thorium in the first stage? Because we already have another fertile material, fertile in the sense that it will be able to produce useful fissile material. So you already have uranium-238, तो अलग से हमको कुछ ऐड करने की जरूरत नहीं है. Like हमारा purpose क्या है? We rely upon closed nuclear fuel cycle. We rely upon spent fuel reprocessing part. That we are trying to recover useful fuel from the first or second stage. So in first stage, you already have uranium-238. So while 235 is undergoing fission, 238 is converting into plutonium-239. So we did not need to introduce thorium, but in second stage we will be using thorium-232. Any other question? Yes. Sorry, in a? Yeah. Yeah. Okay, now that's a good question. In fact, that's also a question which we should know because it was in news a lot. So the question is that we talked about nuclear waste being deposited into water for a few years. That water will become radioactive. Now, how it will become radioactive? I'm going to talk about radioactivity in today's class. But the water which is made of H2O, that H will become radioactive. That one H1, by absorbing some neutrons, it can become 1H3, tritium. And tritium is a radioactive substance, even though tritium is not found naturally. I told you in the last class that deuterium is found naturally, but tritium is not found naturally. Tritium often is produced in nuclear reactors or into specialized setups. We have developed to produce tritium. Tritium is actually quite useful for the very first topic I'm going to discuss in today's class. But tritium is also radioactive. It emits beta particle, and that radioactivity may not be very good. So what to do about that water? Often what is done here is that first this water needs to be purified. We need to extract, or we need to remove as much as tritium as we can, or other type of pollutants as we can. So the same way how in other power plants or other industries, we treat water first. Treatment ka matlab kya hota hai? We are trying to remove the impurities part. So here also, it will be water treatment. It will involve more sophisticated techniques. It will be more expensive, more challenging, but we will do that. But you cannot completely treat such type of water. And then what happens is that this water is often deposited into deep ocean, somewhere into deep ocean. And a lot of environmental groups will always then talk about that how it disturbs marine ecosystem, how it disturbs the nearby marine species. So ye problem hai, that it does cause problem to marine ecosystem because of that radioactive tritium which we are talking about. The only saving grace here is that the amount of nuclear waste which is produced compared to the amount of energy we are producing is very less. Just say, think of 1 unit of coal energy, coal-based energy, and the amount of waste a coal-based power plant will produce. Compared to that, a nuclear power plant will produce like 1,000 times less than waste, but that waste will be very dangerous. So tritium, jo hai, that is actually a problematic thing in the sense that how to deposit it, and it often is deposited into oceans, which causes environmental issues. And why this was in news, in fact, this was in news last year. Kisi ko pata hai kyun news mein tha? Fukushima. So, the Fukushima reactor, when it was destroyed, all of those tankers of water, tritiated water, you'll come across this word tritiated water. Tritiated matlab wahan pe tritium ka jo concentration hai zyada hai. So Japan jo hai, they announced that after a few years they went through treatment, they left the water so that a lot of radioactivity will die down. But then they announced last year that we are going to deposit this tritiated water into ocean. And that led to a lot of fury, particularly in China, because China is one of the biggest buyer of fish from Japan, or in general aquatic species from Japan. So there was a lot of criticism from China. And in fact, China announced that we will not buy any fishery from Japan for some time. Japan ka argument ye tha that jo International Atomic Energy Agency hai, IAEA, which works under UN has proper protocols that what is the safe level of water, what is the safe level of water treatment beyond which you can go and deposit it into the ocean water. We have fulfilled that obligation. But China was furious because the amount of water which Japan deposited into ocean simultaneously, it was a lot, and there was a criticism for that. So this topic, what happens to that water, this actually is also in newspaper and we should know about it. Any other question? So I have few online questions also. Why we go for third stage if we produce uranium in the second stage? I hope that answer is clear now. Third stage, we go because we want to keep producing uranium. And in second stage, we are using plutonium as our fissile material. In third stage, we are using uranium as our fissile material. Can you please explain isotopic separation method? Nobody is going to expect that from you. Isotopic separation method often uses things like laser deposition, chemical vapor deposition. We do not have to go into that. So how do we separate isotopes, let's say uranium-235 and 238? That is not required beyond the scope of this class. Please mention why no moderator is used in second stage again. Yes, I can do that. So why do we use moderators? That is the first thing we should be very clear. We use moderators to slow down speed of neutrons. Slower neutrons have better chances of causing fission. So slower neutrons are better at causing fission. In second stage, we do not use moderator because we want fast neutrons. Now, if we want fast neutrons, then are we saying that we do not want fission? No, we do want fission. But the other reaction, the conversion of thorium into uranium, we are much more focused upon that. And hence the word fast breeder reactor. That uranium production will be faster than fission of plutonium-239, and hence the word fast breeder, that it is going to breed faster compared to consumption of the fuel. So why we do not use moderator? That even though fast neutrons are not good at fission, but fast neutrons are really, really good at converting thorium into uranium. James Webb Space Telescope. Let me complete nuclear technology first. I will explain James Webb Space Telescope. In the last class, you said that no matter can be created or destroyed. What is quark? This question, quark is one of the fundamental particles. We will be talking about this. Not right now. We will discuss about Dr. Satyendra Nath Bose. Bosons के बारे में पढ़ेंगे, वहाँ पे हम leptons, quarks के बारे में भी पढ़ेंगे. So what are quarks? We will talk about that in future classes. In today's class, I'm going to talk about again a very important topic. Give this heading nuclear fusion. Fusion is exact opposite to nuclear fission. In nuclear fission, we started with a heavy nucleus, which was not very stable. We further caused instability to that heavy nucleus by, let's say, bombarding that with neutron. And it disintegrated into lighter nuclei. But it also produced a lot of energy, which we can calculate from Einstein's mass energy equivalence. We discussed that in the last class. In fusion, we do the exact opposite. We start with lighter nuclei. And those lighter nuclei are fused together, merged together to form a heavy nucleus. And the most important reaction, for example, which happens in nature is in the core of stars. I talked about जैसे sun के core के बारे में हमने बात करा पिछले topic में space technology में, that sun has a core. So inside sun's core, a reaction which happens into many stages, but the final end product of this reaction is that 4 hydrogen nuclei fusing together to form helium. It also produces a particle called positron. It can produce energy. And this energy will be, again, we can calculate this energy based on Einstein's mass energy equivalence. E is equal to mc squared, because the mass here in the product will be less than the mass of reactants. So a reaction which happens naturally in the core of stars, where temperature is at 15-20 million degrees Celsius, this reaction is called nuclear fusion. Now we are also trying to have nuclear fusion on the Earth. There has been very limited success in terms of starting fusion, but even more difficult is sustaining fusion, and then trying to produce more energy out of fusion. So we cannot imagine exactly, again I will go back to this thing, that we cannot imagine what fusion may look like at the level of nucleus. But nonetheless, despite that limitation, let's try to imagine that what it might have been. So imagine, for example, 2 nuclei, an hydrogen atom, which has a atomic radius of about some angstrom, I talked about that, and nuclear radius of some femtometer, which we talked about. Femtometer is 10 to the power minus 15 meter. And imagine another hydrogen atom of the same dimension, 10 to the power minus 15 meter and 10 to the power minus 10 meter. And now they are coming close to each other so that they can fuse together. Their protons, neutrons, in hydrogen you do not have neutrons, but they can fuse together and they can produce a heavier nucleus. They can produce heavier nucleus, which is helium. So this type of reaction, imagine how this will look like, that when they are very close to each other, Electrons are very far away from the nucleus. Electrons का जो distance है, that is almost like that if sun is nucleus, then electrons are in an orbit which is orbit of Pluto. If I have to talk about the how many times electrons are far away from nucleus. So electrons are very far away. Compared to 10 to the power minus 15, 10 to the power minus 10 is actually quite a huge value. It is 1 lakh times bigger than 10 to the power minus 15. So electrons are very far away. So when they are going to come close to each other, particularly when they start coming in range of, let's say, few angstroms, then the two nuclei, which are very close to each other, now in the range of few angstroms, they are going to have a very powerful electromagnetic repulsion, because remember, they both have protons here. So if both have protons, we have studied that same charges repel each other. And we also have studied that if I have charges Q1, Q2 separated by distance r, then we have studied that this force is actually looks very similar to gravitational force. Q1, Q2 by r square, with one fundamental difference. This particular constant, we do not have to go into this 1 by 4 pi epsilon naught what it is. That is not important. What is important is its value. It has a value of 9 into 10 to the power 9. The gravitational constant had a value of in the range of 10 to the power minus 11. This has a value of 10 to the power 9, in fact almost 10 to the power 10. So compared to gravitational constant, this is a very, very huge value. And because of that, compared to gravitational force, electromagnetic force is actually a very, very powerful force. Gravitational force is quite weak. Gravitational force only matters when the masses which we talk about, they are of range of few millions and billions of kg, such as one of the object is Earth and one object is Earth, another object is Sun, things like that. But we have mass which is not negligible, but gravitational force among us is negligible, because gravitational force is a very weak force. But electromagnetic force is such a powerful force that to demonstrate that, I just have to rub this pen with my hair and put it on paper, and it will attract that paper. All of us have done that as a child. So electromagnetic force is such a powerful force that to demonstrate it, it needs hardly take a second. So electromagnetic force, be it attractive, and by the way, another thing about electromagnetic force is that it is both attractive and repulsive. Gravitational force is always and always attractive, but electromagnetic force is repulsive also. We know that opposite charges attract, same charges repel. So if two nuclei are very close to each other, then they are going to witness a very powerful electromagnetic repulsion. I will continue this, but let me ask another question here, which some of you already know the answer to. That why is a nucleus stable? That hydrogen में तो चलो फिर भी एक proton है and एक electron है घूम रहा है इसके अंदर. But just go to the next element, which is helium. Now helium has 2 protons and 2 neutrons, and it has, of course, 2 electrons revolving in 2 different orbits. Point is that inside this nucleus, in the range of 10 to the power minus 15 meter, you have protons, and protons are positively charged particles. So, and they are bound in a range of 10 to the power minus 15 meter, बहुत ही कम distance at 10 to the power minus 15 meter. So there is a very powerful electromagnetic repulsion between protons, but still nuclei is stable. Most of the nuclei are stable. Instability only occurs at very high, larger value, or the proton-neutron difference is really huge. Otherwise, nuclei are stable. So why is it so that despite such a powerful electromagnetic repulsion, nuclei simply does not disintegrate or burst out? What is that mechanism which makes nucleus stable? Sorry? So the reason is there is another fundamental force we should know about now. So till now we have talked about 2 fundamental forces. We have talked about gravitational force and we have talked about electromagnetic force. These 2 forces all of us have studied in our school days also. But turns out in nature there are 4 fundamental forces. I'll be talking about the 4th one later. But right now let me introduce the 3rd fundamental force. The 3rd fundamental force is called strong interaction. And this strong interaction actually occurs within proton, within neutron. That proton is not a fundamental particle in the sense that proton can be further divided. If I have a very powerful microscope and if I could see inside proton, then I will look at 3 particles together. Those particles are called quarks. So there was a question, what is a quark? So let me answer that. Quark is what makes up proton or neutron or many other particles. Now quark is a fundamental particle. As far as we know, we cannot divide quark further. Hence the word fundamental particle. Anything which cannot be further divided is a fundamental particle. But proton is not a fundamental particle. If I could see inside proton, I will find 3 quarks. We do not have to go into this detail. The point is that quarks have a very powerful force of attraction, and that force of attraction has a residual effect on the entire nucleus, and that residual effect is called strong nuclear force. So there is a more powerful force, which literally is called strong nuclear force. And that strong nuclear force operates between proton and proton, proton and neutron, and neutron and neutron. Should be very clear that it does not depend upon charge. It is a charge independent force, that it even operates between one neutron and another neutron, one proton and a neutron, and even between 2 protons, which is attractive in this case. So there is a more powerful force inside nucleus, which powerful force is called strong nuclear force. And it is even more powerful than electromagnetic repulsion. In fact, it is more than 100 times more powerful than electromagnetic repulsion. So even though there is a powerful repulsion between protons or among protons inside nucleus, there is a more powerful attraction, which we call strong nuclear force. And that strong nuclear force is responsible for ensuring that nucleus is stable. But strong nuclear force only exists inside nucleus. The moment you go outside nucleus, its value becomes almost 0, negligible. So जो strong nuclear force का जो range है, वो 10 to the power minus 15 मीटर है. Electromagnetic force का range क्या होगा? So gravitational force का range क्या होगा? Up to what distance we can feel gravitational force? Now theoretically it is infinite. Look at this. Force is equal to m1 m2 by r square. So only when r is a very, very large value, this force will become 0. But of course it also will depend upon m1 and m2 there. If m1 and m2 are very high, then gravitational force can be felt up to some distance. Just say, because of us, gravitational force, we do not feel even 1 nanometer around us. But because of Earth, the gravitational force can be felt up to few million kilometers. Lagrange point L1. वहाँ पे भी ऐसा नहीं कि Earth का gravitational force खत्म हो गया था. वहाँ पे Earth का gravitational force was trying to balance out Sun's gravitational pull. So only when you are few million kilometers away, maybe 3, 4, 5 million kilometers away, we can start neglecting Earth's gravitational pull. But think of Sun's gravitational attraction. Sun's gravitational attraction extends to the entire solar system, which is few billion kilometers. And think of now the entire Milky Way galaxy, a compilation of few trillion of stars. And think of this galaxy's gravitational force. That will be even much, it will be in light years. It will be in few light years that we can feel the gravitational pull of the galaxy. The point is that gravitational force का जो range है, theoretically it can be infinite. Practically depends upon what type of mass we are talking about. But theoretically, it becomes 0 only when that r is infinite. But for strong nuclear force, it becomes 0 when r is greater than 10 to the power minus 15 meter. So you do have a very powerful fundamental force in the nature, much more powerful than electromagnetic attraction or repulsion, but it only exists inside nucleus. It does not exist beyond nucleus. So this is the mechanism why nuclei are stable. What about range of electromagnetic force? What is the range of electromagnetic force? Up to what distance electromagnetic force can be felt? Same ही formula है ना? m1 m2 by r square, q1 q2 by r square. So when r is a very large value, then electromagnetic force will become 0. So even electromagnetic force has this range of infinite, right? Theoretically तो यही है, but हम practically कभी भी electromagnetic force की हम बात नहीं करते. The moment we start talking about stars and planets and galaxies, I never talked about electromagnetic force between sun and earth or between galaxies. I only talked about gravity, and I am telling you that electromagnetic force is trillion times more powerful than gravitational force. And I'm still telling you that we do not account for it when we are talking about movements of planets and stars and galaxies. Why is it so? Why do we do that? Think about this question. And it's actually quite simple answer. I will give you a hint. The answer is quite simple. That we do not talk about electromagnetic attraction or repulsion when we talk about celestial objects. Sorry? वो तो gravity में भी है. Gravity में भी force is inversely proportional to distance. Gravity and electromagnetic force का जो nature है, वो बहुत similar सा है. m1 m2 by r square, q1 q2 by r square. Difference है constant का. And electromagnetic force का जो constant है वो ज़्यादा strong है, ज़्यादा powerful है compared to gravitational constant. Sorry, you have to be louder. Perfect, that is the simplest. I told you, simplest answers are often the best answers. Remember another conservation law, which we call conservation of charge. What does conservation of charge mean? That let's say this mouse is electrically neutral. By brute force, I removed some electron out of it and kept it in my fist here. So this mouse has become positively charged once I remove electron. My fist is now has become negatively charged. But as a system, if I include both of this together, they still are electrically neutral. So why we do not account for electromagnetic force when we talk about celestial objects? That on Earth, for example, there will be places where there are positive charges, there will be places there will be negative charges, but on a planet as a whole, Earth is electrically neutral. And same is also true for Sun, and same is also true for the entire Milky Way galaxy. That celestial objects on a larger scale, when we talk about, there can be concentration of charges here and there, some positive charges here, some negative charges there. But on as a whole, they are electrically neutral. And since they are electrically neutral, we do not have to worry about electromagnetic force at larger distances for celestial objects. But electromagnetic force is the most important force in our day-to-day life, because every other force which you have studied, if the word gravity is not mentioned, if the word strong and weak is not mentioned, then it is some manifestation of electromagnetic force, which includes frictional force, it includes viscous force, whatever force you have studied. And you have studied various types of force. All of them are nothing but some type of electromagnetic force. So electromagnetic, all chemical reactions occur because of electromagnetic force. So when we go at atomic and molecular scale, gravity is negligible, because remember, gravity is dependent upon mass. At atomic and molecular scale, mass is negligible, so we do not have to worry about gravity at atomic and molecular scale. We also do not have to worry about the other two forces, strong and weak interaction, because they only exist inside nucleus. They do not exist at the level of atoms and molecules. But we cannot neglect electromagnetic force. At atoms and molecules, there is only one force which is now operational, whose effect we can feel, that is electromagnetic force, and depending upon what type of charges, it can be attractive or it can be repulsive. So when two nuclei are coming close to each other, and they are in the range of atomic and molecular distance, let's say few angstrom, then there is a very powerful electromagnetic repulsion between them. And somehow we have to overcome that electromagnetic repulsion, so that despite this repulsion, they keep coming close to each other. That you had two hydrogen atoms and nuclei trying to fuse together. So despite this very powerful electromagnetic repulsion, they kept coming. And now they form like a structure, something like this. And finally, when they are very close in the range of femtometer now, few femtometer, now strong nuclear force will start operating. And the moment strong nuclear force starts operating, it is going to glue together. So you have two objects which have a very, very powerful repulsion. But the moment they are very close to each other, then this repulsion still is there, but there is a more powerful force which allows them to glue together, which allows them to fuse together. Think of like two friends who had a falling out because of some misconception. लड़ाई हो गई. इतने सारे हिंदी फिल्मों का प्लॉट है. But somehow they found कि नहीं नहीं, we have better relations, and past को देख के they came together. So think of like this, the two hydrogen nuclei who have decided that we are not friends, but when they came very close to each other, they suddenly realized that we are actually quite good friends. And then they came together and they glue together and they form another nucleus, which is called helium. So hydrogen was produced as the first element in the universe, but because of nuclear fusion, helium was produced. And because of nuclear fusion, all other elements were produced. So now let me tell you a few more things about nuclear fusion. When stars start dying, I will be talking about that in later classes. When all of the hydrogen gets exhausted, helium also gets exhausted, and then starts collapsing because of its own gravity. And that collapse leads to such powerful explosion, such high temperature, that it leads to production of all of the heavier elements we know of. So each and every element in your body, it was part of some dying star. So we all are literally made of stars. It's not just a romantic line. We literally are made of stars, that every object, every element in our body, that carbon or that iron or that phosphorus or that sulfur, everything was produced inside a dying star few billion years ago because of nuclear fusion. Sun के अंदर जो nuclear fusion है, that produces helium. From hydrogen, it produces helium. Some carbon can be produced, some nitrogen can be produced, but mostly it is helium because of nuclear fusion. So my starting point here is that nuclear fusion is exact opposite to nuclear fission, which essentially means that in nuclear fusion you have lighter nuclei coming close to each other, gluing together, forming a heavy nucleus. But this will require a lot of energy, because initially when they are coming close to each other, there is a very powerful repulsion, and they have to overcome that repulsion. And to overcome that repulsion, some energy is required, which occurs at very high temperature. And that is why fusion happens at very high temperature. So sun ka core hai, why is fusion not happening on the photosphere or on the chromosphere, in the corona? It is only happening in the core, because in the core, you have temperature in the range of 20 million degrees Celsius, where fusion is possible. And then because of that fusion, this entire stars, all these stars brighten and they produce so much of energy in their vicinity. For example, sun produces so much of energy that life is possible on planet Earth. So one more thing, that without nuclear fusion, life is not possible, because without nuclear fusion, there is no brightening of star and there is no life here. There is no energy and there is no life on the planet Earth also. So nuclear fusion is also responsible for the life on this particular planet, or maybe on other planets also. So these are some of the basic things. Now we are trying to replicate the process on Earth. We are trying to conduct fusion-based experiments. And उसके बहुत सारे benefits होंगे अगर वो जब भी possible हो जाए, जब भी हम उसको sustain करा सके. So we'll be talking about the benefits and what will be the challenges, but first write down few things here. Nuclear fusion is the process. Nuclear fusion is the process by which lighter nuclei combine to form a heavy nucleus. When it happens, huge amount of energy is produced. When it happens, huge amount of energy is produced, which can be calculated, using Einstein's mass energy equivalence, E is equal to mc squared. E is equal to mc squared. This is the process. This is the process which powers sun and other stars. This is the process which powers sun and other stars. In the core of star, hydrogen fuses together to form helium. Write down next paragraph. For fusion to occur, nuclei have to overcome electromagnetic repulsion. Repulsion to the extent and range strong nuclear force starts operating. We will have a discussion about fundamental forces in later classes, not right now. But we will talk about fundamental forces in more detail, about gravity, about electromagnetic force, strong force and weak force. So till the range strong nuclear force starts operating, which glues nuclei together. Last line, which glues nuclei together. Because of this, because of the energy required to overcome repulsion, fusion occurs at very high temperature. So what are we trying to do on Earth then? We are trying to conduct fusion for quite some time now, and there has been some success here and there. But till now there is not a single fusion-based reactor which can commercially produce power, which can commercially produce energy and fulfill our energy requirement in our households. That has not been possible, even though there has been some milestones, and I'm going to talk about those milestones also. So what are we trying to do first? How do we ensure that we can generate temperature in few million degrees Celsius so that fusion can happen and we can capture that energy and we can fulfill our energy requirement? So there are two main approaches which are being adopted. And in both the approaches, we are not trying to fuse Hydrogen, we are trying to fuse two isotopes of hydrogen. Deuterium, tritium, I talked about the three isotopes. So one is hydrogen, one H1. But on Earth, jitne bhi experiments ho rahe hain, all of them are trying to do this. They are trying to fuse deuterium and tritium so that it can produce helium and neutron. And of course, it is going to produce energy because of Einstein's mass energy equivalence. This will be M1, this will be M2. M2 will be less than M1. The rest mass has been converted into energy. This is the reaction we want to have on Earth. But for this reaction to occur, we need to create conditions where temperature and pressure is so high that deuterium and tritium, it can fuse together. So there are two approaches which has been adopted to conduct fusion. Right? One of the most famous approach is called tokamak. Tokamak is a type of experimental reactor. As of now, many countries have their own tokamak. So tokamak is type of an experimental reactor. And this will be a schematic diagram of tokamak. So this will be a toroid shaped device, kangan ki tarah. ऐसे समझ लो kangan है. So imagine a kangan. So this will be a toroid shaped device. And inside this toroid shaped device, we will create perfect vacuum. There will not be a single air particles. And then with the help of powerful superconducting magnets, we are going to increase the energy of, we are going to increase the temperature of hydrogen, not hydrogen, deuterium and tritium. So we will have deuterium and tritium inside this at very high temperature where deuterium and tritium exist in plasma state. Have I talked about plasma before? I mentioned plasma as the fourth state of matter. When objects become at such, they come at such high temperature that electrons often come out of the atomic and molecular bond, and then they coexist with the positively charged ion. So this negatively charged particle electron coexist with positively charged particle. So you can think of plasma as a gas which is ionized. If you want to imagine plasma, आप ऐसे imagine कर लो कि gas है but जो ionize हो रखा है. Ionize इसलिए हो रखा है because इसके पास electrons के पास इतना energy है that they have come out of the atom. So very similar to gas, plasma has no fixed shape, size, will occupy volume in whatever room. But plasma is ionized. It is positively charged particles and negatively charged particles. Inside this toroid, inside this perfect vacuum, we are going to produce very, very powerful magnetic field. Those who have studied about magnetic field in class 11th physics, will you tell rest of the class that what magnetic field does to charged particle? What is the impact of magnetic field? How many of you have studied physics in class 11th? A few of you. So what does magnetic field do to charged particle? Sorry? But what type of, so that is a very generic answer. I want more precise, like what will be the actual impact of magnetic field on charged particles? Change its direction. Perfect. So very simple. If there is a magnetic field, जैसे मान लो that in this on this board, I have this, in this particular direction, I have magnetic field coming out of the board. इस तरीके से imagine करो that I have some magnetic field. I am going to denote this with dot. And if a charged particle enters inside this magnetic field, so it will experience a force, but there is a thing about magnetic field. Magnetic field cannot increase your kinetic energy. It cannot increase your speed, but it can change your velocity. So it is a force, but it is a force whose impact on charged particles will be that if it is a constant magnetic field, then it cannot accelerate you. Sorry, it can accelerate you, but it cannot actually increase your speed. So what is going to happen, you're going to move in some sort of circle here. You'll come in circle and you'll come out. So if, let's say you started with some speed v here, then you're going to maintain the same speed v, but you're going to move into a circle. This is the impact of magnetic field on charged particles. I only have to talk about this information. So just Those who haven't studied physics in class 11, just in one line, remember this thing, that magnetic field, it cannot increase kinetic energy, it cannot increase the speed or decrease the speed, but what it can do, it can change the velocity. It can deflect charged particles. It can allow them to move into, in fact, even a circle or even a helical position. So that is the impact of magnetic field. So what happens inside a tokamak? Tokamak is also called, if you look at the heading here, magnetic fusion. So why the word magnetic fusion? That inside this perfect vacuum, we create plasma of deuterium and tritium. But this plasma is ionized particle, charged particle. Charged particles can be guided with the help of magnetic field. We keep increasing the energy by help of, let's say, superconductors. There can be some other mechanism. There is a use of laser also. There are many ways. But as the temperature starts going into few million degrees Celsius, this plasma has enough energy that the moment it comes in contact with any of the walls, the entire wall is going to vaporize. So even a very small plasma which exists at, let's say, 10 million degrees Celsius is going to vaporize this entire wall here. It has so much of energy. We do not want that to happen. We want to ensure that this plasma keeps on moving in the perfect vacuum without coming in contact with the walls of the tokamak. For that, we will use magnetic field, because even though magnetic field cannot accelerate, but it can guide its path. It will keep this plasma, the two, perfectly suspended in the vacuum of this toroid. This shape is called toroid. So you have this perfectly suspended plasma inside this toroid, and when temperature is enough, when it reaches to few million, in fact 50, 100 million degrees Celsius also, then now this deuterium tritium plasma will start fusing together and will start producing helium. It is going to produce energy. That energy will be absorbed by the walls of the tokamak, and with the help of water or something else, we will keep removing that energy from the walls of the tokamak. So the working of tokamak is that let's use very powerful magnetic field so that we can contain deuterium and tritium plasma at very high temperature, at very high pressure, inside a perfect vacuum chamber, so that the temperature, when it becomes sufficiently high, fusion starts and it starts producing energy. So this is the mechanism, first mechanism, which has been operational, there are so many designs, so many countries working towards this particular design, including India, by the way. So even India has its own tokamak situated in Gujarat, and it is operated by an institute called Institute of Plasma Research. So this is one design. जो tokamak word है, ये Russian word है, इसका full form कुछ Russian में होगा जो हमको याद रखने की कोई ज़रूरत नहीं है. But one of that will be some impact of magnetic field, something like that. So this was designed by few Russian scientists, and this has become quite popular. One of the operational tokamak, which will become operational in next few years only, is this particular design. There is an organization called ITER. International Thermonuclear Experimental Reactor. Fusion often is called thermonuclear fusion because it happens at very high temperature. Temperature requirement itna zyada hai that we use often this word thermonuclear fusion. This International Thermonuclear Experimental Reactor is a collaboration among many countries. Many countries have come together. They have pooled their resources. They have pooled their talent. And then they are working towards construction of the world's largest tokamak, which is situated in France, in southern France. And when it becomes operational, it aims to attain fusion power of 500 megawatt. And whatever learning which will happen in this reactor, tokamak reactor, that will be shared with rest of the member nations. So India is one of the member nations. So ITR is a collaboration among many countries. You have US, you have Russia, US, Russia again working together. You have China, you have Japan, you have South Korea, entire European Union, UK, and then India. So you have many developing nations and almost all of the Western world part of this collaboration, pooling their resources, pooling their talent, and working towards the largest construction of tokamak, But even before this, there are many other tokamaks which already are active. जैसे in Europe you had a tokamak called Joint European Torus, JET. In China, you'll come across this word China's artificial sun. सुना है किसी ने newspaper में कि China के पास कुछ artificial sun है. So that artificial sun is nothing but a tokamak device. It is a tokamak device, and the reason we are calling it artificial sun because it aims to conduct nuclear fusion inside this particular tokamak. So China's artificial sun is nothing but a tokamak which aims to contain that plasma and aims to attain fusion. And even India का जो पहला tokamak था, so that we called it Aditya tokamak. So Aditya also its sun. So जो आदित्य टोकामाक है उसका पर्पस सिर्फ ये था that let's try to contain plasma, that can we contain plasma in a vacuum chamber, and that successfully was demonstrated. So as of now we have upgraded things, and the current tokamak which India has, it is called SST2. There was SST1 and now we have SST2, which basically means steady state superconducting tokamak. So SST2 is also tokamak. So many countries, despite the fact that they are member of ITR, they're also investing a lot of resources in their own country. That because we were not going to wait for ITR के results. ITR के results होंगे, you have some key ideas which we got to know, and you immediately are ready for nuclear fusion based power. Now all of this has been going on for last 30-40 years, by the way. It's not a new venture. The focus on nuclear fusion has been happening for last 30-40 years. And you have very little success to show, and millions of dollars have been poured into this venture. Not just ITR, but many other venture which different countries have adopted. Millions of dollars have been poured, and you have very little success to show, which raises a question that why are countries investing so much amount of money in tokamak or in nuclear fusion device? I will come to that question also. So that is the first design. You can write it down. आप लिख सकते हो, write down in next paragraph or give this heading. Nuclear fusion based power on Earth. Nuclear fusion based power on Earth. There are mainly two approaches. There are mainly two approaches. First is called magnetic confinement fusion. And इसका जो सबसे बढ़िया एग्जाम्पल है, आप इसी में लिख लेना, is a tokamak. Right down here. In this approach, fusion fuel ब्रैकेट में लिख लेना ड्यूटेरियम एंड ट्राइटियम is heated to form a plasma. This plasma is confined. Using powerful magnetic fields. To keep it from coming in contact with the walls. Uses powerful magnetic fields to keep it from coming into contact with the walls So tokamak hai, this is a toroid shaped device which aims to do that. That shape which we show is called toroid. Write down examples. The first example is IT year. International Thermonuclear Experimental Reactor. International Thermonuclear Experimental Reactor. Write down. It is a collaboration among many countries. It is a collaboration among many countries, including India, including India, including India. It is world's largest tokamak under construction. World's largest tokamak under construction. Under construction. Situated in France. Situated in France. You can watch this YouTube video. The name of this video is "We Went Inside Largest Nuclear Fusion Reactor." It's hardly 8-minute video. And look at the construction, what is happening here. You'll get to see the type of tokamak which they're trying to build. So it's hardly 8-9-minute video. You'll get the video also talks about little bit about fission, and then goes on to explain fusion, but essentially shows you the construction, that what will this tokamak look like once it is fully operational. This is a collaboration among many countries, and India is part of this collaboration, by the way. The most important thing which we should know from nuclear fusion. You can also know about this device called yeast. Experimental Advanced Superconducting tokamak. And this is what is popularly known as China's artificial sun. A very popular tokamak. Joint European Torus. So European countries, they are part of ITER, but they have their own tokamak called Joint European Torus, which is situated in UK. India इसका member नहीं है. ये mostly this is a collaboration among European countries. You also have this SST का मतलब यहाँ पे steady state superconducting tokamak. So you have this institute called Institute of Plasma Research, which operates under Department of Atomic Energy. And हमारा जो capability है in fusion, that is actually quite limited. So as of now, we haven't even started nuclear fusion. Our goal here is to contain plasma. And अभी initial goal हमारा ये होगा that let's keep raising the temperature. Plasma first, let's try to contain that at few thousand degrees Celsius, then at few lakhs degrees Celsius, and finally at few million degrees Celsius. And once we can contain plasma in the vacuum chamber, then we will go to the next step, which will include starting the condition where nuclear fusion is possible. So we should know about Institute of Plasma Research and these 3 experimental setups which India does have. SST2 is the latest one. तो पहला अप्रोच है, इस बहुत पॉपुलर अप्रोच है, जो टोकामाक अप्रोच है, an older approach and a very popular approach. In America, there are many such experimental reactors, but in America, they have adopted a separate design altogether, and that design has actually proven to be successful. And that design is called inertial confinement. So the first design was magnetic confinement. In California, there is a lab called Lawrence Lab. Lawrence Lab is quite a like secret lab in the sense everybody knows about the lab, but very few people know that what is happening inside the lab. It essentially is defense lab. So US, in terms of military technology, US of course is the most advanced country. And one of their facility here is, within Lawrence Lab, there is a facility called National Ignition Facility. And the purpose of this National Ignition Facility is to successfully achieve nuclear fusion, but their design is very different. So how this design is different? That in a chamber, where in a very small location, in a very small device, you have deuterium and tritium kept here. And then you illuminate this region with this laser beam. All these which you can see, these are laser beams, about 200 laser beams. 200 laser beams perfectly balanced from each and every direction, and all of them are pouring their energy at just one point. Now whatever is at this one point, it cannot explode, and if you cannot explode, you implode then. Implode का मतलब, explosion का मतलब होता है throwing away outward, implosion मतलब होता है going inward. So if in all direction the forces are balanced perfectly, that you cannot explode because of high energy, but then the other option you do have is this implosion. And this they have been doing for quite some time. That let's use laser beam and let's contain that deuterium and tritium, not with the help of magnetic field. The reason we are using here inertial fusion, because we do not want this deuterium tritium to travel. We do not want this to move inside some vacuum chamber. We want it to be stationary, and we are going to implode that with many, many laser beams together. And then fusion is going to happen and energy will be produced. Last year, in 2022, this lab announced a news which became front page of all of the newspapers, that they have successfully achieved surplus energy using fusion. Now what does that mean? Nuclear fusion people have done many times. Many countries have been successfully able to conduct nuclear fusion. The problem with nuclear fusion is that to start nuclear fusion, you need to produce lot of energy. You need to have lot of energy. And then you hope that the energy which is going to be produced because of fusion will be much, much more than the energy which you consumed. Think of this like as a business. You invested 100 rupees and you're hoping that I'm going to get 150 rupees out of it. But if you have invested 100 rupees and all the time you are getting 80 rupees or 70 rupees, that's not a very good business. So before Lawrence Labs announcement, fusion was exactly this, that everybody was investing 100 rupees, that everybody was investing 100 joule of energy, and the energy they were getting was 50, 60, 70. But Lawrence Lab made an announcement that at a very smaller scale, at a scale of this one, a device, deuterium tritium located in this device, and they were able to conduct fusion, and they were able to produce surplus energy. So for the first time in the world, using nuclear fusion, surplus energy was produced. I will repeat, fusion has been possible many times in many nations. But for the first time, fusion allowed surplus energy production. By the way, that does not mean a lot abhi tak, because we have figured out the science part. Again, remember, we have figured out that at such smaller scale, we can produce surplus energy. But how to scale it up now? How to now make a device using this static fusion which can produce energy in a sustainable manner for, let's say, an entire city? Now, that will be the second challenge, and it is going to take a lot of time. So we still have to figure out the engineering part, that how we are going to scale it up and how are we going to ensure that it can become a sustainable source of energy for an entire city. So we should know also about inertial fusion, because this is the only setup, again I will repeat, till date, more than 2 years have occurred since this announcement, and till date, it is the only setup which has produced surplus energy using nuclear fusion. तो आप लिख सकते हो about inertial fusion. It is achieved by compressing and heating. It is achieved by compressing and heating small pellets of fusion fuel, small pellets of fusion fuel, again same, deuterium and tritium, bracket में लिख सकते हो, deuterium and tritium, small pellets of fusion fuel using intense energy from laser beams. Using intense energy from laser beams. The rapid compression and heating, leads to a condition where fusion is possible. Fusion is possible. For example, you can mention this lab, Lawrence Lab in US had successfully conducted inertial fusion, and produced surplus energy for the first time. Using nuclear fusion. So this news is also important, although ये 1.5 साल 2 साल पुराना news है, but after that they have done it twice or thrice also, so this topic remains in news. The goal here will be now to scale it up so that we can produce fusion based energy on a much larger scale. But then I will go back to an earlier question which I asked, that we are pouring so much of amount of money, and we का मतलब I'm talking about all countries, by the way. जितने भी countries के पास fusion based facility है, they are pouring lot of money, and it almost seems like that lot of this money is going into vain. Fusion always seems one step ahead. जैसे आज से 10 साल पहले भी न्यूज़ यही था कि 10 साल में फ्यूजन हो जाएगा, और अभी भी न्यूज़ यही है कि 10 साल में फ्यूजन हो जाएगा. So it always seems like that we are trying to solve some problems, but fusion still remains some sort of like elusive technique which we are not able to achieve. So the question then comes here is that why are we so much after nuclear fusion? What is it about fusion that so many countries and so many companies are interested into nuclear fusion setup? So give the next heading. Advantages of nuclear fusion. Advantages of nuclear fusion. Full form of DAE is Department of Atomic Energy. जो मैंने लिखा था इंस्टीट्यूट ऑफ प्लाज्मा रिसर्च अंडर DAE, DAE का मतलब है डिपार्टमेंट ऑफ एटॉमिक एनर्जी. एडवांटेजेस ऑफ न्यूक्लियर फ्यूजन. एक चीज जो न्यूक्लियर फिशन और फ्यूजन दोनों में कॉमन है, that they both are clean source of energy. Clean in the sense that they do not produce greenhouse gases. Both fission and fusion, remember fusion maybe there is no greenhouse gas. So you have clean source of energy that it does not produce greenhouse gases. That is one common thing. But whatever challenges we talked about fission, none of those challenges are present in case of fusion. So both produce clean source of energy, do not produce any greenhouse gases. Fission में क्या डर था? Nuclear waste का डर था. Fusion में end product क्या है? Helium है, neutron है, which will be produced with very high energy because of the fusion based energy. That energy we have to capture with the help of water, with walls, have to produce electricity. But helium is not a radioactive substance, and so is neutron. So we do not have to worry about that long-lived radioactive waste which we talked about, nuclear fission. दूसरा डर क्या था fission में? That fission can lead to reactor meltdown, an uncontrolled chain reaction. If we are not able to control the reaction, it can lead to a meltdown, it can lead to a nuclear accident. Fusion requires, पहले तो fusion chain reaction है ही नहीं, सबसे पहली चीज. Fusion is not a chain reaction. Fission is a chain reaction. And fusion requires so many prerequisites that if any of those prerequisites do not get fulfilled, fusion stops, tokamak stops, nothing happens. So there is no fear of any reactor meltdown here. Second thing. Third thing, fission का fuel क्या है? Uranium है. Uranium mining in itself is hazardous, which is problematic. Fusion का fuel क्या है? Deuterium है. Now deuterium is found in every natural source of water. Tritium is not found in water, but tritium can be made into lab with the help of hydrogen or helium or something else. That will require energy, but nonetheless जो mining related problem है वो fusion में नहीं है. Another benefit of nuclear fusion. We do make fusion based weapon. जैसे आपने कभी कभी term एक सुना होगा hydrogen bomb. सुना आपने? What is hydrogen bomb? Does anyone know? So I explained atomic bomb in the last class. That atomic bomb based on nuclear fission. Now hydrogen bomb नाम से तो clearly पता इतना तो पता चल जाना चाहिए that we are talking about a fusion based bomb. So few countries do have this capability. US definitely has hydrogen bomb. Even Russia has hydrogen bomb. Maybe even China has it. North Korea claims, but that claim may be false. Few countries do have hydrogen bomb. Now what is a hydrogen bomb? Hydrogen bomb essentially is two bombs put together. First, it is an atomic bomb. First trigger will lead to an explosion, and that will be because of nuclear fission. But that will be a small trigger, a small amount of energy. That nuclear fission based bomb will produce so much of energy that now it will lead to nuclear fusion. At very high temperature, fusion can happen, and that will lead to the second explosion, which will be much, much more dangerous and disastrous than the first. So we do have a weapon based on fusion, but the only commonality here is that both of that uses fusion. In terms of design, engineering design, it is very different. While in case of fission, think about it, you enrich uranium for reactor also, you enrich uranium for atomic bombs also. The only difference is the enrichment percentage, while in reactor 3, 4, 5%, in atomic bomb 90%. But process same है यहाँ पे. Fusion में process बिल्कुल अलग है. जो hydrogen bomb based बनाने का तरीका है, वहाँ पे कोई हमारा goal ही नहीं है that we want to control, we just want to cause as much as destruction as we can. So the only common here is the science part. The process is very different. The engineering is very different. Hydrogen bomb is an altogether separate design. Tokamak is altogether a separate design. inertial fusion is altogether a separate design. So if a country is investing into tokamak, into inertial fusion, you do not have to worry about that maybe they are doing that for developing an atomic bomb. But if a country is enriching uranium, then you have to worry about that maybe they are doing that for atomic bomb. Just right now there is a lot of allegation against Iran that they are enriching uranium to make an atomic bomb, right? So that is another benefit, that you do not have fear of nuclear proliferation if somebody is investing into tokamak or inertial fusion. And last but not the least, that both fusion and fission have very high energy density. I have talked about that, the amount of energy fusion produces versus fission, fission produces versus other source of energy. But fusion has more energy density than fission, many times more. It's not even a small difference. 1 kg of hydrogen or 1 kg of deuterium tritium undergoing nuclear fusion and 1 kg of uranium undergoing nuclear fission, fusion will produce more than 10 times or even 50 times in fact energy than nuclear fission. So that is the last but one of the most important benefit, that fusion produces more energy for the same amount of fuel compared to nuclear fission. That is why so many countries and so many organizations are so bullish about fusion. That yes, there are challenges. We have to create conditions where fusion is possible first. We have to sustain conditions where this continues. We have to also think about tritium, what to do with tritium, because tritium is radioactive. So there are certain challenges, but if we can overcome those challenges, then we have a source of energy which is sustainable, has no issue of mining related problem, and does not produce any greenhouse gas. For hundreds and hundreds of years, this can become a source of energy without worrying about any other source of energy, coal, natural gas, petroleum, whatever. We do not have to worry about any other source of energy. And that is why fusion is such a big deal. तो आप लिख सकते हो both fission, हाँ जी, first fission then fusion. Because when we talk about nuclear fission, the question, one of the fear of nuclear fission based, मान लो कोई country fission पे invest कर रहा है, they have to enrich uranium. Other countries will say that maybe you are doing that because you are enriching uranium for developing a nuclear weapon. And ऐसा भी नहीं कि theoretical है. Past में इंडिया पे allegations लगे और इंडिया ने nuclear bomb develop भी किया. ईरान पे भी allegations है that Iran is enriching uranium, and Iran already has announced that they have achieved enrichment of about 70%. So enrichment process is the same, that isotopic separation method is the same. The difference is the percentage part. So science हमारा क्या है, atomic bomb का nuclear fission है. Process क्या है, enrichment है. तो in atomic bombs, the science and process, they both are same. In hydrogen bomb, science is same, yes, both will use fusion, but process is very different. In hydrogen bomb, the process involves first fission, which will trigger a fusion. We do not want to control anything here. We want to cause as much as destruction as we can. In fusion-based reactors, such as tokamak or inertial fusion, which I just explained, they do not aim to have uncontrolled explosion here. The process here is very different. They do not even go into fission. Tokamak mein kya hai? That deuterium tritium plasma, let's contain that with the help of magnetic field. Inertial fusion, use laser beam, have nuclear fusion. So nowhere we are talking about nuclear fission here, right? So that is how the process is different, even though the scientific principle, it's same, nuclear fusion in case of hydrogen bomb, right? Write down few things here. Both fission and fusion are clean source of energy. Both fission and fusion are clean source of energy. That is, they do not produce greenhouse gases. That is, they do not produce greenhouse gases. They do not produce greenhouse gases. However, fusion has many additional advantages. Fusion has many additional advantages. Many additional advantages. Write down in bullet points. For same amount of fuel, for same amount of fuel, for same amount of fuel, fusion produces much more energy than fission. Fusion produces much more energy than fission. Fission. Next, there is no fear of long-lived radioactive waste. There is no fear of long-lived radioactive waste. Radioactive waste. Third, there is no fear of meltdown. There is no fear of meltdown because fusion is not a controlled chain reaction. Fusion is not a chain reaction. Fusion is not a chain reaction. Fusion is not a chain reaction. And also, it requires many prerequisites. It requires many prerequisites. If any parameter does not matches up, fusion stops. If any parameter does not matches up, fusion stops. Next, fusion requires deuterium. Fusion requires deuterium. Deuterium, which is available in all natural source of water, which is available in almost all natural source of water, which is available in almost all natural source of water. And tritium, which can be made into lab, all of these benefits of fusion you can mention if there is a question about nuclear fusion benefits. Challenges हैं, मैंने benefits पे highlight इसलिए करा है because it should be very clear that पहले तो fusion करा लेना, which is only going to be possible at very high temperature, which you need to create conditions where such high temperature can exist. But such high temperature also has to be contained. Either you use inertial confinement or magnetic confinement, you decide that. But it has to be contained, because if it cannot be contained, then it will lead to an explosion which will cause a lot of destruction. That is the second thing. Third thing, then you need to sustain fusion. Sustain fusion so that as fusion happens, it produces more and more energy compared to the amount of energy you started with. So all of that condition, you need materials which can handle all of that. When all of that condition fulfills, then you have fusion. So saying that on piece of paper and attaining that actually in a practical setup, in a lab setup, are two different things. And that is why fusion has been such a huge challenge. And despite decades of work, there are very limited milestones which human beings have to show in case of nuclear fusion. So this is a topic which, according to me, is an important topic, both for prelims or mains perspective. If you have any questions, you can ask questions now. There is a very good question. When it does not increase the speed, then what's the reason for the acceleration? For that, we can use other mechanisms. We do use superconducting magnets, but the use of superconducting magnets is very different from the confinement part. I will not go into that part. We can also use laser here. to accelerate things, but that's not required here. Does helium also combine to form lithium like hydrogen combine to helium? Almost all elements which we see on Earth or anywhere in this universe for that matter, almost all of them, if not all of them, are result of nuclear fusion happening inside stars. There are elements not because of fusion, but because of radioactivity they can occur. So that is also a possibility, but many elements, almost all elements, including the iron and calcium and carbon in your body, that is a result of nuclear fusion which happens inside stars. Do electrons contain positive charge as it is in the news? What news is that? I will have to read that. In celestial bodies, they have mass, which means that they have charged particles. So how is it neutral? Remember that charge जो है वो electrons के कारण है. Electrons have negative charge, remove and protons के कारण है. Remove electrons, you have excess of protons compared to electrons. But electron को remove करके क्या करोगे? कहीं ना कहीं तो रखोगे ना? So if electrons have been removed, ऐसा तो नहीं कि electrons have disappeared. Those electrons are somewhere. So that is why celestial bodies as a whole, they are electrically neutral. That even if you do remove negative charged particles, they are somewhere. The only thing is that concentration of negative charged particle has increased somewhere, and consequently, it has also led to a place where concentration of positive charges have increased. But net on net, they still are electrically neutral. Sorry? What is protium? 1H4. What is protium? So hydrogen. Okay, so why hydrogen has not been used? Hydrogen has not been used because hydrogen का जो nuclear size है वो बहुत कम है. And because of that जो electromagnetic repulsion है, it will stay there for longer duration. So to combine hydrogen, you need to overcome much more electromagnetic repulsion. जो deuterium का nuclear size है वो ज़्यादा है. And because of that strong nuclear force which actually allows that two nuclei to glue together, that will start operating earlier. So you have to overcome less electromagnetic repulsion. But in case of hydrogen, you have to overcome more electromagnetic repulsion. So that is why we do not use hydrogen. Doing that, the deuterium, tritium on Earth, that is easier. Okay, there are some methods to do that. The question is that how do we convert this energy for usable energy? Jैसे in case of tokamak or in case of inertial confinement also, whatever energy will be produced, it will be the kinetic energy of helium or neutron which is being produced. We can make a container around it, and that container keeps absorbing these neutrons or helium. Because of that, you have more and more atomic vibrations in the container. The container internal energy increases, its temperature increases. Now what we can do here is we can use water around the container, on the surface of the container, and the water which we allow to flow, that will be at low temperature, but the water which will come out will be at high temperature. The same thing we did in case of nuclear fission. That in the core, fission was producing a lot of energy, which was heating up the core, and we were now transporting that heat away from the core with the help of a coolant such as water. So we can do the same thing here also. That we have to build a container which can absorb neutrons of very high energy, and because of that the entire container heats up, but we have to keep absorbing that heat with some mechanism here, so that we can use that heat to produce electricity. Sun has also both fission and fusion. As far as we know, Sun only undergoes fusion. Fission produces less energy fuel than fusion. Also you said 2 years ago, surplus energy. Not getting this, semi-contradictory. Two different things. What I said theoretically, when we look at the mathematical calculations, when we look at the reactions, when we do mathematical calculations, we see that every 1 kg of hydrogen, or every 1 unit of hydrogen and 1 unit of uranium, that hydrogen fusion will produce more energy compared to uranium fission. That's one statement. The second statement, that we produced surplus energy for the first time, that's a separate thing. Do not try to juxtapose two things which are not related per se. So the second thing, when I said that for the first time we have produced surplus energy, it simply means, go back to my starting of the class. I talked about that how for fusion to start, I need a lot of energy. So I need to start with lot of energy. It's like that Hindi muhavra, normal tel hoga na radha nachegi. So you need to start with lot of energy. If you do not have that lot of energy, you cannot have nuclear fusion. So you start with lot of energy, and then your hope here is that once nuclear fusion happens, it is also going to produce energy, and that energy which has been produced should be much, much more than energy which has been consumed. So I started with some energy E1. Fusion happened because of this energy. Fusion produced E2, and this is only a very good deal if E2 is greater than E1. And by the way, one more thing, it shouldn't be simply greater than, it should be much, much more greater than E2. There is a reason that even though E1 energy will be, E2 energy is being produced, will you be able to utilize all of that energy? The answer is no. There will always be loss of energy. So even if I, let's say, assume an efficiency of, let's say 70%, which is very high efficiency, that the energy we produced was E2, we were able to utilize 70% of that energy. So in a way, that 0.7 times E2 should be greater than E1. Not just E2 should be greater than E1, E2 का कुछ fraction जो है 0.7 E2, that should be greater than E1. That if I started with 100 and I produced 120, but 120 का efficiency 80% है मान लो. 120 का 80% is 96. So I started with 100 but I got 96. I do not want that, right? So जैसे अब एक सिंपल सा एग्जांपल ले लो, आपने 100 रुपए से बिजनेस शुरू करा, आपने प्रॉफिट जनरेट करा 150 रुपीस, आपने सेल्स आपका हुआ 150 का, सो आपका 50 रुपी प्रॉफिट है, बट सडनली गवर्नमेंट आ गई और गवर्नमेंट ने बोला कि हमको टैक्स चाहिए 40%. वहाँ पे आप ये बिजनेस बिहार में कर रहे हो, वहाँ पे लोकल रंगदार हैं, देर आर बाहुबलीज देयर, मैं बिहार से हूँ, आई कैन क्रैक दिस जॉब. So let's say that there are local bahubalis there, and local bahubalis are saying that we need some protection tax here from you. Those who are from Bihar, they will know what am I talking about. So by the way, Bihar badnaam hai har jagah ye. So anyways, so you have to give energy. So now when you account for all of the money which you are giving away, salaries, everything, turns out that that 50 rupees profit तो खत्म हो ही गया, you had to pour some extra money from your pocket. That's also not a good business. So fusion requires to produce energy which should be produced should be much, much more than energy you started with, so that even with some efficiency, let's say 60-70%, that energy is more than the energy you started with. That is the meaning of surplus energy. And that was achieved for the first time at National Ignition Facility situated at Lawrence Lab. So this is about nuclear fusion. I think this much information is more than enough. Let's take a break here. After that, we'll discuss the last part of this entire discussion. Okay, the question is just a second. एक question है इनका कि fusion होने के लिए कितना temperature चाहिए? ये question इतना आसान नहीं है. Fusion होने के लिए ideally जो temperature चाहिए वो होना चाहिए 100-150 million degree Celsius. So the ideal temperature for fusion to happen is 100 million, more than 100 million degree Celsius. Stars का जो core है वो 20 million degree Celsius पे है, फिर भी वहाँ पे fusion हो रहा है, right? So I told you that जो core of stars है, the temperature is at 20 million degree Celsius. So that even at that temperature, how is fusion possible? To appreciate that, you actually need to know some knowledge of quantum mechanics and a phenomena called quantum tunneling. So fusion occurs in star because of very, very low probability event, which is associated with something called quantum tunneling, not required here. But on Earth, if I want fusion to occur, then I need temperature more than 100 million degrees Celsius, which essentially means we are talking about temperature higher than the core of this star, even though in a very limited range, at a very limited location, but I do want temperature more than core of this star. So if there is a statement that for fusion to occur, we need temperature more than the core of the star, that will be correct statement. आप इस तरीके से इसको सोच लो, ठीक है? चलो, I will see you guys. Sorry, class खत्म नहीं हुई है. I will see you after the break, and we will discuss radioactivity. Any questions if you have from whatever we have discussed? Yes. We cannot use any material to hold that energy. The energy which will be produced will be because of kinetic energy of neutrons and the helium which is being produced. That neutron, helium, it is going to be absorbed by the nearby walls, which will heat up the container, the wall, and there from there we can absorb that heat with use of some sort of coolant or something else. So once we do produce energy, then our goal is not to contain it. Our goal is to utilize it. And yes, that is also very difficult thing, that once we do produce energy, how to utilize that to fulfill our electricity requirement. And for that, we have to rely upon materials which can readily absorb neutrons and helium, and we can utilize that energy somewhere. The last part of this entire discussion about nuclear technology involves another natural phenomena, which you should know about. This natural phenomena is called radioactivity. If you want to make notes about radioactivity, make running notes. I'm not going to dictate anything. But I do think we should know about the concept of radioactivity. In the last class, in today's class also, I told you that how some nuclei are not stable. And I also mentioned that this instability or stability is because of configuration of protons and neutrons inside nucleus. Some configurations are more stable, some configurations are not very stable. So there are certain nuclei which are not very stable, but a natural tendency of such nuclei will be to attain stability. This in general is a fundamental law of nature, that objects try to minimize their energy and they do try to attain stability. So nuclei also try to attain stability. They want to become something else where they have less energy and where they are more stable. So there are some natural processes, and three natural processes which actually happens. That let's assume a random nuclei called X, which has atomic number of Z and atomic mass of A. X can be anything, Z, A is the atomic number and atomic mass of this particular nucleus. This nucleus is not very stable. In one way it can attain stability, that it can emit from inside the nucleus, it can emit a particle, and the particle is called alpha particle. But that alpha particle is nothing but a helium nuclei. It essentially is helium nuclei. That from inside of the nucleus, a helium nuclei will be removed from inside of this nucleus. So from inside nucleus, I had Z protons, but 2 of the protons I have removed. So this becomes Z minus 2 now, whatever is left. Think of this like as a reaction, but this is a decay reaction. To be more precise, we call such reaction decay reaction, that things are decaying. So I started with Z, but 2 protons are removed, it became Z minus 2. But if it is Z minus 2, no longer it is X. It should be very clear that the word atomic number, when we use, for every element there is a specific number of proton, and which is called atomic number. So if I started with atomic number Z, but now it is Z minus 2, it is clearly not X, it has become something else, let's call that Y. And 2 protons, but 2 neutrons also have been removed, so its atomic mass is also going to decrease by 4. So I can call this a parent nucleus, I can call that a daughter nuclei. If you want to imagine it, आप ऐसे समझ लो how iron reacts with oxygen or moisture in the atmosphere and starts rusting, which is a natural chemical reaction. This is a natural nuclear decay reaction where an unstable nucleus which wants to attain stability, and in order to do so, releases a particle called alpha particle. We call it alpha, but it is nothing but a helium nucleus. And when that happens, it will convert into something else. Maybe that Y is stable. Maybe that Y is not stable. If that Y is not stable, it will convert into something else, either by emitting another alpha particle or by emitting some beta particle. So it can emit alpha or beta, it can become Z, it can become some A, B, C, whatever. But it will keep on happening till the point of time it finally has attained a stable nucleus. So radioactivity, जो process है which happens naturally, it leads to final, जो final हमारा result होगा, वो एक stable nucleus होगा, which is not a radioactive nucleus. The best example which I can tell you about radioactivity, one of the known elements which undergoes alpha decay, I have talked about uranium-235. Uranium has atomic number of 92. Uranium-235 found in nature is not very stable. I already have mentioned that. In order to attain stability, it often emits an alpha particle, which decreases its atomic number to 90. I told you 90 kiska atomic number hai? Thorium ka, so this becomes thorium, but atomic mass becomes 231. So alpha decay of uranium-235 produces an isotope of thorium with atomic mass of 231, atomic number of 90. We are not doing anything, this happens in nature. Wherever you have uranium-235, some uranium all the time is getting converted into thorium by emitting alpha particle. If this thorium is not stable, it will emit another alpha or another beta particle. So what is beta particle? So this ये जो reaction है, this is called alpha decay reaction. Then let's assume that you have another radioactive nucleus. Let's again call it X, atomic mass Z, atomic number Z, atomic mass A. And now it emits a beta particle. Now we call it beta, but it is either an electron or a positron. Positron looks very similar to electron with this fundamental difference that it has positive charge. They are exactly same in each and every aspect, but their charges are different. I will be talking about this concept in later classes. They are called particle and antiparticle to each other. So positron is antiparticle of electron. Don't worry about it right now. Just remember that positron is a particle very similar to electron with one fundamental difference, that it has positive charge. It has same mass, same every other property, it's same, but its charge is different. Beta decay happens into 2-3 stages. It does not happen, this becomes something else, that becomes something else, but the end result of that is that it will produce something which now has atomic number Z plus 1. Again, if it is Z plus 1, no longer it is X, it has become some Y, but nothing happens to atomic mass. Atomic mass remains the same, but atomic number increases by 1. This is beta decay. So in a way it is producing an isobar. Look at it. Isobar का definition क्या था? Same atomic mass, but different atomic number. So यहाँ पे you have same atomic mass, but it is different atomic number. The best example of beta decay which happens in nature, I can tell you about, is that you have carbon, जिसका एक isotope है 14. Carbon 14 जो है, carbon 14 जो है, this emits beta particle. 6 becomes 7. Now 7 is what? Nitrogen. So carbon converts into nitrogen. This is the reaction, by the way, which we use for carbon dating. All of us have studied this method called carbon dating to calculate age of a particular fossil. I'm going to explain how does that happen, that how do we actually do this. But the underlying mechanism of carbon dating method is this particular reaction, decay reaction, an example of beta decay. There are many other radioactive nucleus which undergo decay and they emit beta particle. The third type of reaction, often this daughter nucleus, so I started with uranium, I'm going to call it parent, I'm going to call this daughter. So often this daughter nucleus has lot of excess energy. It has very high energy, particularly the nucleus has very high energy. And in order to attain stability, it will release that energy by emitting what we call gamma particle. Now gamma particle is light, it essentially is light, but it is not visible light. It is not that red, blue, green color which we see. This light is not even X-ray. X-ray is dangerous than visible light. X-ray जहाँ पे भी आपने देखा होगा हॉस्पिटल में एक्सरे होता है, देयर विल बी वार्निंग साइन दैट एक्सरे रूम में या एक्सरे डिवाइसेस के पास ऐसे आप रैंडमली अलाउड नहीं होगे. But turns out that there is even more powerful radiation than X-ray, and that is called gamma ray. So gamma ray is also a type of light, an electromagnetic wave, a photon. The fundamental difference is that gamma has much, much more energy than any other light we know of, including X-ray, including ultraviolet light. You have studied about that how exposure to ultraviolet light can cause cancer. पढ़ा होगा आपने ozone layer के बारे में जब भी पढ़ा होगा, you must have studied that ozone layer filters out the dangerous ultraviolet light, and by doing so it actually helps us that we do not suffer from trachoma or from skin cancer or some other genetic disorder. So UV light is nothing in terms of the damage it can cause compared to gamma ray. So जो gamma ray radiation है, that is very, very dangerous. You also must have read about this, that how in Hiroshima and Nagasaki many children were born with deformity even many years after those two atomic bombs in 1945. पढ़ा होगा आपने, right? The fundamental reason here is that gamma radiation. That gamma radiation can cause genetic deformity, it can induce mutations, and it can cause genetic deformity. So gamma radiation is a very, very dangerous radiation. But gamma radiation is not some combination of protons and neutrons and electrons. Gamma radiation, मान लो again I start with some X, atomic number Z, A. I'm going to use a star here. Star here signifies that it has a lot of energy. It emits gamma. Nothing happens to its atomic number. Nothing happens to its atomic mass. But it loses that energy. इसका जो excess energy है, that excess energy has been released in the form of a light photon, which we call gamma. And that gamma has very, very high frequency and very high energy. Exposure to gamma radiation, a very high dose can immediately kill a person, a horrible death. And even a very small dose, but for some long duration, it can easily cause cancer or various other type of diseases, including genetic deformities. So gamma radiation is a dangerous radiation, and this occurs because of radioactive nucleus. So all of the nucleus which can emit alpha, beta, or gamma, they can be called radioactive nucleus. And often we use the word radioisotopes for them because, but clearly they are not very stable. There is some stable version, and hence the word radioisotope in this particular case. So radioactivity is a natural phenomena. It happens in nature all around us. All of the elements, all of the nuclei which are not stable in ocean, on the surface, in the atmosphere, all the time they undergo this spontaneous decay by releasing alpha particle, which is helium, by releasing beta particle, which is electron or positron, or by emitting gamma particle, which is type of a light, but light of very, very high frequency. We cannot see that, but it is a very dangerous type of light, very dangerous photon because of its high frequency and high energy. So we do not have to do anything here. All of that happens naturally. That is the first thing we should know, that there are certain nuclei which are not very stable, and they undergo this spontaneous decay reaction by releasing what we call alpha, beta, or gamma. And ये जो पूरा process है, this process is called radioactivity. Radioactivity will often lead to transformation of one nucleus, one atom, into something else, particularly if it is alpha or beta. If it is gamma, it will not lead to transformation into something else, but nonetheless, it will produce lot of energy. It will produce very high frequency energy, dangerous energy in fact, energy which is not often desirable. In most of the cases, it is not desirable. Do we have? Almost all of the daughter nuclei which are being produced, they will have lot of energy and they will emit gamma. In very low dose of gamma radiation, it actually has lot of applications. So high dose of gamma radiation is dangerous, but very, very low dose which is manageable. We know that it will not cause any damage. It has applications in many areas, and this is what I'm going to explain in this entire discussion about, last discussion about nuclear technology. But even alpha and beta emission had certain applications which I'm going to talk about. That is the first thing, that there is something called radioactivity we should know, which is nothing but alpha decay, beta decay, or gamma decay. The second thing which you should know about radioactivity, that it follows a very interesting rule. Let's say that I started with some parent nucleus, which converted into Y by emitting either alpha or either beta. That X is becoming Y in some time t. Let's say that when I started this calculation, I have a sample here. I have collected a sample of, to be more precise, let's say I have uranium 235, 92, and it is converting into thorium 231, 90. I have some sample of uranium 235, which is disintegrating, it is decaying into thorium. When I started my calculation, the total number of nuclei in my sample, let's say, was n. It goes without saying that this n will be a very large number. I already have established this, that even if I have a very small amount of uranium, even 250 gram of uranium, that n will be in the range of 10 to the power 23, trillions to trillions of nuclei we are talking about. So this n will be a very, very large value. Let's say in some time t, half of uranium converted into thorium. So only half will be left. So after some time t, I only have n by 2 number of uranium nuclei. अगर मान लो कि ये linear decay होता, if it would have been decayed linearly, what does that mean? If the graph, let's say that on y-axis I am representing n, on x-axis I am representing time t. When I started my calculation at time t is equal to 0, this was the number. After some time capital T, it became n by 2. It came here. If it was a linear decay, if this decay followed a straight line graph, then in another time t, this would have become 0. So in time t, n became half n by 2. In another time t, it became 0. If it was a linear decay, but turns out it is not a linear decay. So radioactivity hai, it follows a very interesting rule. That rule is called logarithmic decay. You do not have to worry about that word. But what it means is that in next time t, it will not be 0. Whatever is left, half of that will decay. So after time t, n by 2 was left, but n by 2 ka jo half hai, wo n by 4 hai. So after next time t, n by 4 will be left. After next time t, n by 8 will be left. After next time t, n by 16 will be left. So it will come very close to 0, but theoretically, it will never become 0. Theoretically, it is never going to become 0. That time t which I have shown here, this time t is fixed for every sample. Uranium 235 ka jo time t hai, and by the way, this time t is called half-life. There is a reason why we call it half-life, that in one half-life, half of this sample is disintegrating from parent. It is disintegrating into, not disintegrating, but decaying into some daughter nuclei. So if I start with some very large number, after every capital time t, it becomes half and half and half and half. And which essentially means is that theoretically it will not become 0. And for every sample, जैसे ये uranium 235 है, turns out uranium 238 is more stable, but not that stable. Even uranium 238 decays into thorium. So I can also have this alpha decay for uranium 238. This also becomes thorium, except that it produces an isotope of thorium with atomic mass of 234. तो ये जो टाइम t है, यूरेनियम 235 का जो टाइम t होगा कुछ अलग होगा, जो यूरेनियम 238 का जो टाइम t है वो कुछ अलग होगा. So half life of every radioactive nucleus is different, and we can calculate that half life. We know that half life or of many of the radioactive nucleus. So many of the naturally occurring radioactive nucleus, we know what is their half life. Half life simply means that in that time they keep on decaying into something else. So I start with some number x. In that time t, it became x by 2, x by 4, x by 8, x by 16, and so on and so forth. So every radioactive sample has a fixed half-life. No matter where you go, that half-life does not change. That half-life can vary from few days to few million years. तो ये जो variation है वो बहुत ज़्यादा है. That there are certain radioactive nuclei which occur naturally. They often decay into few days. Half of that, let's say, decays into 30 days. Another half in 30 days. Another half in 30 days. But there are certain radioactive nuclei which decays into few million years. That I started with some sample, but in few million years, they became half. In next few million years, they became half. So half-life has a huge variation. First thing. Second thing, we can now produce radioactive nuclei into a lab condition. So there are many naturally occurring radioactive nuclei, but there are specific type of reactors. One of the most famous is called cyclotron. At such reactors, we can often produce subatomic particles like electrons or protons or neutrons at very high energy. And in a lab condition, I will start with some stable nucleus, and I will bombard them with some very high energy particles, and this will lead to a nuclear reaction. And because of this nuclear reaction, we will be able to produce a radioactive nuclei. So there are many radioactive nuclei we can produce into lab. I will have to start with something else. So what we are doing here is that I take some A here, that A was stable, that A was bombarded with neutron or with proton or electron, it became B, but this B becomes now very unstable. This B becomes radioactive, and when this B becomes radioactive, it will start emitting alpha, beta or gamma particle. In lab, we have been able to produce radioactive nucleus, जिसका half life जो है वो 1/1 million second में है, in a fraction of second. That, let's say, in 1/1 million second, half of that disintegrated. In next 1/1 million second, another half got disintegrated. So for all practical purposes, the time 1 second happens, almost all of that sample will, almost all of the parent nucleus will decay into daughter nuclei. So naturally occurring radioisotope, the half-life can vary from few days to few million years. But lab-made radioisotope, the half-life can be as small as 1/millionth of fraction of second. And all of this understanding of alpha, beta and gamma decay, it has actually allowed various types of applications in many, many areas, right? I will start with the very first one and the most popular one, which you already know, that how carbon dating functions, right? So let's talk about this, how carbon dating works. Again, I'm not going to make you write anything. If you want to write, make running notes. That's how carbon dating works. Carbon dating works on many assumptions. There are many assumptions in carbon dating, but those assumptions, we have very good reasons to believe that why those assumptions are true. The first thing we should know here is that where does carbon-14 come from? Carbon is quite a stable nucleus, and carbon का जो सबसे prevalent जो form है वो carbon-12 है. All of us are made of carbon-based life. All living organism is made of carbon. जितने भी biomolecules हैं हमारे body में, be it proteins or carbohydrates or nucleic acid, whatever, or lipids, fats, all of them are nothing but made of essentially carbon. We are organic molecules. We are combination of organic molecules which somehow understands about other organic molecules. Think about it. We are not very different from any other type of matter, but somehow this particular composition understands about other type of organic molecule. So we are, and we ka matlab I'm talking about all living organisms, we are made of carbon-12, but we are also made of a little bit of carbon-14. So if a tissue is analyzed, if for example in a lab I deposit some of tissue, even 1 micrometer of tissue, and even that 1 micrometer will have trillions of carbon atoms, goes without saying. So when this will be analyzed into a lab setup, you'll find that there are some carbon-14 also. It's not that my carbohydrates and my proteins and my nucleic acid are only and only carbon-12. Some of that is also carbon-14. But where did that sum of carbon-14 come from? Now this is interesting. So where does carbon-14 come from? Carbon-14 comes from cosmic bombardment of neutrons that Earth is receiving as a planet. जो Earth का outer atmosphere है, that is receiving neutrons from many sources. From sun also, but also from distant stars and galaxies. And that constant bombardment of neutrons into upper atmosphere. In atmosphere, the most important gas is what? Nitrogen. Nitrogen is 78%. So that nitrogen undergoes a transformation, a nuclear reaction. Because of that neutron, this neutron is a very small particle compared to a nitrogen atom. It can enter inside a nitrogen nucleus, and it can convert that nitrogen nucleus into carbon-14. We are not doing this. This is happening naturally. That all the time, some nitrogen is getting converted into carbon-14. And this has been going on for last few million years. ऐसा नहीं कि कोई नया phenomena है. This has been happening for last few million years. That nitrogen getting converted into carbon. But turns out this carbon-14 is radioactive. This carbon-14 undergoes this reaction. It again converts back into nitrogen. That ये फिर से nitrogen में बदल जाएगा. शुरुआत हमने nitrogen से किया. From nitrogen, carbon-14 was made. All of this is happening naturally. We are not doing anything. And that carbon-14 again is decaying back to nitrogen-14. But here is a catch. It has a half-life of about 5,800 years. Exact half-life is 5730. I'm going to approximate that to be, let's say, 6,000 years. So that we can remember it. 5730 will be difficult to remember. So carbon-14 has an approximate half-life of, let's say, 6,000 years. What it means is that if I start in a sample with carbon-14, then every 6,000 years, half of that carbon-14 will decay into nitrogen. In next 6,000 years, another half. In next 6,000 years, another half. So where did carbon-14 come in my tissues? All of that comes from photosynthesis. Because remember, all of the life starts from photosynthesis. Life essentially starts from plants doing photosynthesis. जो primary producers हैं, जो green plants हैं, they are the only organism which can capture sunlight, and in the presence of some inorganic molecule like carbon dioxide and water, they can make carbohydrate. ये तो सबने पढ़ रखा है ना class 9th के science में, that CO2, H2O reacting in the presence of sunlight and forming a complex molecule which we call carbohydrate. But CO2 plus H2O is a chemical reaction. ये जो 6 CO2 plus 6 H2O in presence of sunlight जो हमने पढ़ रखा है, that is a chemical reaction. It's not a nuclear reaction. And chemical reactions only and only depend upon what? Outermost electron, जो outermost shell में जो electrons हैं. So चाहे वो carbon-12 हो, चाहे carbon-14 हो, number of electron तो दोनों में same है. It has 6 protons, 6 electrons. What differs is neutrons. Carbon-14 has 8 neutron. So इन दोनों के chemical property में difference नहीं है. इन दोनों के nuclear property में difference है. And this is a chemical reaction. So when plants absorb carbon dioxide, then they are not only absorbing carbon dioxide, carbon made of 12, but they are also doing carbon made of 14 atomic mass. So when photosynthesis is happening, it is not happening for 12 CO2, it is also happening for 14 CO2. ट्वेल्व का मतलब यहाँ पे कार्बन का एटॉमिक मास है. And plants cannot distinguish between carbon-12 and carbon-14. So whatever ratio of carbon-14 divided by carbon-12, this ratio, let's call this ratio as n. N बहुत small value होगा. It should be very clear that this n is a very, very small value. But whatever ratio is found in atmosphere, the same ratio is found in plants also. And because all other living organisms are dependent upon plants, we eat plants. Some animals eat plants, we eat those animals also. So whatever you are a herbivore, you are a carnivore, doesn't matter. But you essentially are dependent upon the biomolecules stored by plants. जो हमारे biomolecules हैं, they essentially come from biomolecules which were made by plants. So whatever ratio is in the atmosphere, the same ratio is in plants, and the same ratio is in all living organisms. And that is why I said that if I take even 1 micron meter of my tissue, then the carbon-14 and carbon-12 ratio will be same, almost same, what is found in the atmosphere. Now, the assumption here is that this ratio n which I have written here has not changed a lot in last few 100,000 years. That is an assumption, and we have very good reasons to believe why this assumption is true. Because the amount of neutron bombardment which occurs in the upper atmosphere, that does not appreciably increase or decrease. So on an average, the amount of neutron which bombard outer atmosphere is more or less same. So amount of carbon-14 which is being produced is more or less same. So amount of this ratio, carbon-14 and carbon-12, that does not change a lot, or that hasn't changed a lot in last few 100,000 years. And the same ratio which is found in atmosphere, the same ratio is found in plants, because plants do photosynthesis. And since we eat plants or we eat animals, those animals also eat plants, food chain. So the same ratio is found in all living organisms, as long as you are alive. The moment you die, now what is going to happen? The moment you are going to die, lot of your flesh will be decomposed. वो काम का नहीं है. But some of the organic molecule, particularly your bones, can survive even for hundreds of thousands of years. If your fossil is conserved because of, let's say, low temperature, whatever it is, if a particular sample has been conserved because of environmental condition, decomposition did not happen, then we take that fossil, we look at that what is the ratio of carbon-14 and carbon-12 there. Now remember, as long as I am alive, the ratio carbon-14 by carbon-12, that ratio n, it's same as atmosphere. The moment I am dead, carbon-14 is stable, not radioactive. Nothing is going to happen to carbon-14. But carbon-14 is not stable. Carbon-14 is going to decay. So carbon-14, in every 6,000 years, half of the carbon-14 has become nitrogen. So once, as long as I am alive, I have ratio n. But when I am dead, after 6,000 years, that ratio became n by 2. Carbon-14 कम हो रहा है, carbon-12 सेम है, तो रेशियो क्या हो जाएगा? n से n by 2 हो जाएगा. In next 6,000 year, basically after 12,000 year, that ratio is going to become n by 4. In next 6,000 year, which is 18,000 year, this ratio is going to be n by 8. So all I need to do now is that whenever I have collected a fossil sample, I need to just look at how much is the ratio of carbon-14 and carbon-12. And I already know that if something was alive here, then what would have been the ideal ratio when something was alive? And what is the current ratio? And how much time it will take for that n to become n by some number, n by, let's say, m or something. And ये बहुत simple mathematical calculation है. It's a very simple calculation which will show you that once you have a fossil, how old this is. So carbon dating works only and only because of living organism. If I have some rock which had no life, a bare rock, which never had a life, which is, by the way, very difficult on planet Earth. Planet Earth has been flourishing with life for last few billion years. So it's very difficult. But let's say that you have a bare rock with no life, carbon-14 is not going to work there. Carbon-14 only tells you that on a particular fossilized record, when was something last alive. And to do that, we are using the concept of radioactivity. This will, however, only work if you have a fossil of, let's say, few thousand years old, 50,000, 60,000, at max 100,000 years old. अगर उससे ज़्यादा old है, तो problem होगा. Because ये जो decay reaction है, this became n by 2, n by 4. This will go something like this. So it will come very close to 0, but it will never become 0. Let's say this is a plot of carbon 14 by carbon 12, and this is the plot of time t. When something was alive, this was the ratio. Let's say this is n here. When I collected that sample 6,000 years later, I found this n by 2. I immediately know that ये 6,000 साल पुराना है. I found it n by 4 or somewhere in between. I know that ये 12,000 साल पुराना है, ये 18,000 years old है. But if it starts coming here, 50,000, 60,000, इनके बीच का जो difference है, ये बहुत कम है. और यहाँ पे margin of error आपका बहुत ज़्यादा है. So if you have a sample which is very old, let's say more than 100,000 years old, carbon 14 is not going to work. But carbon 14 is quite accurate if you have a fossil which is not that old and you want to know that what is the approximate time that something was alive in this fossilized record. So we use the concept of radioactivity, particularly beta decay of carbon 14, to know about how old a particular fossil is. So this is how carbon 14 dating works. We are using the natural process of radioactivity. We are not doing anything here. हमने कुछ नहीं करा है. We understand what is happening, and based on that understanding, we are trying to use to calculate age of a particular fossil. But in lot of things, we actually try to produce radioisotopes into lab, and then we use that into different areas, and that is my topic here, starting with, let's say, applications in agriculture. So give this heading, nuclear technology applications in agriculture. Nuclear technology applications in agriculture. Achha, I have a request here that particularly to those students who haven't, let's say, studied science after class 8th, 9th or 10th, and you're feeling a lot of difficulty in such cases, then come and meet me after the class. And what we can do here is that we can have some special sessions where we will, rather than studying, we will just have a discussion about brushing up the basic scientific concepts, which is given in your, let's say, class 9th and 10th NCERT. I will have to talk to classroom team if it is feasible or not, but I do think it should be feasible. So I am very sure that some of the students may find it very difficult to suddenly grasp the concept of radioactivity or whatever we have discussed till now. So in such cases, we can have some special session where rather than I am making you dictate things or something like that, we will have a discussion. And with the help of that discussion, we will try to brush up the basic concepts which already are taught in school days in class 9th and 10th. Right? So meet me after the class if you are suffering from this problem, that you are not able to comprehend a lot of things. Right? If you're not able to comprehend few things, that's totally fine. It's a technical topic. Uska simple solution hai, that you go and watch the same thing again. एक बार में बहुत जो कॉम्प्लेक्स टॉपिक्स होंगे वो बहुत बार एक बार में ग्रास्प करना मुश्किल होगा. पॉलिटी नहीं है, सिंपल ये पॉलिटी नहीं है, ये बेसिक इकोनॉमी भी नहीं है. यहाँ पे एक कॉन्सेप्ट को ग्रास्प करने में टाइम लगेगा, आपको पढ़ना पड़ेगा बार बार. एंड द मोर यू स्टडी यू विल रियलाइज दैट ओके नाउ दिस इज मेकिंग मोर सेंस एंड इट इज लॉजिकल, इट इज मेकिंग मोर सेंस. We can have the same for online students, do not worry. So if we can have a special class, even online students, I will have to talk to classroom team if it is feasible or not, but I do think something like, and maybe if we have few students from different batches, we can have a combined class here also. So we can have that, we will just have to, I do think it is feasible. So even for online students, you can be part of online, and whatever your doubts are, we can discuss that with the help of response portal only. So write down, give this heading, applications in agriculture. The first is mutation breeding. Does anyone know with agriculture or biology as background that this term mutation breeding, what exactly it is? Sorry? How? Genetic manipulation, how? Okay, now we are on to something. Hybridization can be a very good example of mutation breeding. Mutation breeding का देखो क्या मतलब है? all of us, there's a few basic concepts of biology all of us are very clear about, that we share our genes, we inherit our genes from our parents. That is why many of our properties, how we look like, or some of our properties, they come from our parents, either mother or father. But in the course of our lifetime also, we go certain spontaneous changes. Those changes are called mutations. That our DNA, जो हमारा genetic blueprint है, that undergoes certain changes in our lifetime, and those changes are called mutations. Mutations are essential for species to evolve. When we talk about evolution of species, mutations are essential because some mutations are good, some mutations are bad, many mutations are simply neutral. They do not do anything good or bad per se. How mutation happens? Mutation can happen when your cell divides. Then within that division, DNA is really good at making a perfect copy of itself. When one cell divides, it creates 2 copies of DNA exactly identical to each other. And it is really, really good at that. But there is 1 in billion chance that it will cause an error. That this division is not 100% perfect division. There is a minor error. And that minor error will lead to a mutation, a change, a genetic change, which in many cases will be neutral. In some cases it can be harmful. In other cases it can be helpful. One of the leading cause of cancer is bad mutations. That when cells mutations are bad, it can lead to erratic division of cell, which can lead to a tumor, which can spread to other part of the body also, which we call cancer. But mutations can be helpful also. Some mutations can be helpful. That is the first thing. Mutations happen naturally, but mutations can be increased. The rate of mutations can be increased. How they can be increased? If you are exposed more to chemicals, if you are exposed more to pathogens, even when you get infected by viruses and bacteria, they can cause changes to your genetic structure. Not all of them, not all the time, but in certain cases it is possible. And particularly if you are exposed to radiation. So if you are exposed to UV light. So when we say that UV light can cause cancer, then it is nothing but some bad mutation. आपने पढ़ा है ना कि UV light can cause skin cancer. So that is nothing but some bad mutation, that it altered your gene in a way which is not desirable, which is dangerous. But UV light से ज़्यादा जो dangerous है वो X-ray है, and X-ray से जो ज़्यादा dangerous है वो gamma ray है. So if you are exposed to gamma ray, then that can also alter your genetic composition. It can cause mutations, and many of those mutations can be bad. It can cause cancer. It can also make you Hulk if you have watched Avengers movies. But it can cause, that's only science fiction. It can cause bad mutations. It can cause cancer. So we have done mutation breeding since we knew about agriculture. What you talked about, hybridization, that we have always experimented with developing hybrid crop. Taking 2 variants of a crop and trying to develop something interesting. 2 different genetic varieties of rice and breeding them together to develop a new variety of rice. The hope here is that maybe that new variety has desirable properties. You cannot control what type of properties that new variety will have. You do know that it will have some of both of the varieties we have utilized. The same way, a parent cannot control that what type of properties their child will acquire, even though it is their genetic properties. The same way when we do mutation breeding, we cannot control what type of properties we are actually going to get. So in mutation breeding, what we do, we take plant buds, we take seeds, and we expose them to gamma radiation. That exposure to gamma radiation will cause mutations. Many of those mutations will be harmful. We are going to discard that. But some mutations can be desirable. Maybe one of that mutation can be that this seed or this plant bud can grow in less water, or is tolerant to drought or salinity, or has high productivity, things like that. So whenever we are doing mutation breeding using gamma radiation, this will be an application of nuclear technology in agriculture. And remember, gamma radiation कहाँ से आएगा? That will come from radioisotope. Gamma radiation ऐसे available नहीं है. उसका जो source है, it is some radioisotope. The most famous radioisotope which we use in lab condition is called cobalt-60. So cobalt-60, cobalt का जो एक isotope है, 60, that is one of the best source of gamma radiation which is available to us. So mutation breeding using nuclear technology includes, आप लिख सकते हो, exposing plant buds and seeds, exposing plant buds and seeds, plant buds and seeds, to gamma radiation, exposing plant buds and seeds to gamma radiation, which can induce mutations, Some of those mutations can be desirable. Some of those mutations can be desirable. Some of those mutations can be desirable, such as resistance to drought and salinity, high productivity among others. So I will repeat this. Mutation breeding, mutations are natural process essential for evolution. In this particular process, we are escalating this natural process. By exposing plants, buds and seeds to gamma radiation, we are hoping that maybe some of the variants will be desirable. But we cannot actually control what type of property we are going to get from mutation breeding. This is in contrast with when we use the word gene editing. So in biotechnology, you'll be taught about gene editing. You'll be taught about techniques like CRISPR-Cas9 or TALEN or ZFN. These techniques alter a very precise, at very precise location, it can alter your DNA, and that can introduce a very precise type of property. So gene editing leads to type of desirable. You can actually have much more control over what type of properties you want to acquire. But in mutation breeding, that is not possible. So this is one application. Another application can be in food processing. Food processing is very simple. How to enhance shelf life of food? We have to kill microbial organisms inside them. I cut an apple, put that on a table. This apple is going to rot in a day or two. Same apple I put inside fridge, it is going to survive for 4 or 5 days. The reason is very simple, that at very low temperature, जो microbial activity है, bacteria and fungi, they do not divide, they do not multiply as much they can. So every living organism, including bacteria and fungi, they need optimum condition for their survival and for their reproduction. At very low temperature, bacterial and fungal reproduction does not occur at very high rate, and because of that, your food can survive. But another way how you can improve the shelf life, that what if you can kill microbial organisms which already are part of your perishable items such as fruits and vegetables. Let's use gamma radiation. We use ultraviolet light also, but we can use X-ray also, we can use gamma ray also, we can also use beam of electrons, by the way, that these particles or this radiation, it can kill microbial organisms without altering the nutritional value of food itself, and you get to enhance the shelf life. So this is already used in many cases, and no, it is not dangerous, because it is only dangerous, remember, it is not introducing radioactivity to your food item, it is just causing damage to the microbial organism. People often fear that gamma radiation making food dangerous. Will it compromise the nutritional value? So even cooking food compromises the nutritional value. Remember that the moment you cook food, it compromises on the nutritional value. So here also, yes, there can be some minor changes, but nonetheless, this is a very popular practice. And Department of Atomic Energy in India has proper guidelines that whenever we do something like this, what is the process you have to follow. So use of gamma radiation for food processing is actually quite a popular technique. आप लिख सकते हो, exposing food items to gamma radiation. There is a question that in सब में न्यूक्लियर टेक्नोलॉजी कैसे यूज हो रहा है. ये जो गामा रेडिएशन है वो रैंडमली नहीं होगा. गामा रेडिएशन का जो सोर्स है वो रेडियो आइसोटोप है. रेडियो आइसोटोप in itself is understanding of nuclear technology. The concept of radioactivity very much fits into the nuclear science and nuclear technology. So how nuclear technology has applications in all of that? Because to produce gamma rays, we need some radioisotope, which is part of nuclear science and technology. तो आप लिख सकते हो, exposing food items to gamma rays, X-rays, UV light, or even electron beams, can kill microbial organisms, and enhance the shelf life of food. ये जो टेक्निक है exposing food to radiation, these techniques are called food irradiation. आप लिख सकते हो, these techniques are called food irradiation. Give the next heading, applications in medicine, or applications in healthcare. Applications in healthcare. The first and the most important one is cancer treatment. Write it down. External beam therapy, proton beam therapy, internal beam therapy. This is called brachytherapy. I'm coming to that. So cancer treatment, let's say for example somebody suffers from advanced stages of cancer. Cancer has spread to many parts of the body. Then doctors do a lot of things. Cancer treatment is one of the most mentally excruciating process for the patient as well as for the entire family member. So cancer treatment jo hai. So it includes a lot of things. Let's say a tumor which has grown into size a lot has become cancerous. Then doctors will first apply lot of medicines, chemicals to shrink the size of tumor, which we call chemotherapy. But chemotherapy has a lot of side effects, which will lead to a lot of nausea all the time, falling off hair, everything. But after that, when the tumor size has shrinked a little bit, doctors will then operate on that tumor, will remove that tumor. Second part. Third part will include this external beam therapy. So external beam therapy now includes that if there are traces of tumor left, something which has not been removed even after the surgery, then it will be exposed to gamma radiation. Gamma radiation from let's say cobalt-60 low doses of gamma radiation, which can destroy the remaining parts of the tumor. The goal here is that once it is removed completely, cancer will not bounce back. It often happens that patients, particularly in advanced stages of cancer, cancer does bounce back. There is a often recess of cancer, and doctors use external beam therapy to particularly ensure that that does not happen. It may not occur all the time. It may not be like effective all the time, but it is a very important part of protocol of the cancer treatment. So that why we are calling it external beam therapy, that we are using this externally. A mechanism which may look something like this, that you have high energy radiation by this device. We locate a tumor and we expose gamma radiation to the tumor directly so that the tumor or whatever part of tumor that can be destroyed. It goes without saying that it will have a lot of side effects. It is also going to destroy a lot of healthy cells, and it will have a lot of side effects. कोई doubt भी नहीं होना चाहिए. So proton beam therapy है, that is also an example of external beam therapy, but rather than using gamma, we use beam of protons. But remember, even beam of protons can only be produced from some nuclear reaction. So beam of protons का फायदा ये है that protons will deliver all of their load specifically at the tumor, and उसका जो side effect होगा वो बहुत minimal होगा. But proton beam therapy is much more expensive and available at very few locations. Just I'm talking about in India, it is available at very few locations. Very specialized hospitals have this proton beam therapy. जो brachytherapy है, that is a more sophisticated technique. In brachytherapy, we use a radioisotope and we place it inside the body near the tumor itself. That a tumor has grown somewhere, and you place a radioisotope inside the body so that this radioisotope can emit gamma radiation of very low dose and can only destroy the tumor part. Hence the word internal beam therapy. That here we are not exposing gamma radiation externally. We are placing a radioisotope near the tumor itself, where it can destroy tumor and we can actually save the healthy cells here. It goes without saying that internal beam therapy or brachytherapy is not applicable in all type of cancer. It is only and only applicable in very localized cancer. Cancer has spread to many parts of the body, it's not going to work very well. So brachytherapy has limitations, but uska benefit ye hai that if it is localized, then with very less side effect, the tumor can be treated. So all of these methods which I mentioned, brachytherapy or external beam therapy, or proton beam therapy, all of them are for cancer treatment, and all of them, unka jo essential science hai, that includes changes which are happening at the level of nucleus, hence application of nuclear technology. But it is not just in application of disease, application of treatments, also in diagnosis we use it. So the next application can be nuclear medicine. So by the way, coming back to the earlier point, that it may seem like a difficult topic to comprehend, but even if whatever we have, even if you can grasp some part of it, if not all, if you can grasp the basic part of whatever we are discussing, and whatever we are writing down, plus some handouts I'm going to give it to you, that will be much, much more than enough for both prelims and mains question. I have shown you questions from space technology. In fact, let me show you some of the question from nuclear technology asked by UPSC. This was a question asked last year only. 2023 का question है. क्या होगा आंसर? I want more responses. Is this clear to everybody that why answer is C? Second statement is not correct. Uranium enriched to the extent of at least 60% is required for the production of electricity. That is not correct. But statement 1 is true. India, despite having uranium deposits, depends on coal for most of its electricity production. That is true in case of India. So questions will not be very difficult. Questions will be quite simple, quite straightforward. There will be quite a rarity where question will be very technical and something which cannot be attempted per se. Science and technology prima facie looks like a difficult topic, particularly if you do not have a background in the topic. But I promise you that when all the aspirants, and I'm talking about aspirants who are serious about their studies, when they go, then science and tech is exactly same for everybody. Very few aspirants, for example, unless I have some expertise in or some background in, let's say, physics, then topics of physics will be perhaps simpler for me. That's it, topics of physics will be simpler. Lot of topics of technology, of ICT, of biology, biotechnology, they are exactly same as for rest of the candidate. So science tech के questions attempt करना सबसे simple है. This is one of the topic which will require one-time effort, and yes, a lot of effort. That goes without saying. That effort, initial effort will be lot, but it will be much, much more rewarding because you do not have to mug up things here. You understood the basic concept, you can answer questions. Questions hardly are factual questions there. Most of the questions are analytical questions which can be logically deduced and we can find the correct answer. And in mains it becomes even easier. Mains may understanding of applications, limitations, challenges, how to write it down, it becomes even easier. Prelims difficult इसलिए है because बहुत open-ended सा syllabus है, इसलिए difficult है. But जो questions हैं वो खुद में difficult नहीं है. Questions बहुत ज़्यादा simply attemptable questions हैं. Let me show you more questions. Not asked by UPSC. Few questions I have made here, but this was a question asked by UPSC. ये 2017 में आया था शायद. Is everybody clear that answer is D here? India is an important member of International Experimental Thermonuclear Experimental Reactor. If this experiment succeeds, what is the immediate advantage for India? It is about nuclear fusion. There is only one option which is talking about fusion. Rest of the options are not even talking about fusion. Thorium in place of uranium, satellite, efficiency of fission reactor, it can build fusion reactor. Answer is D here. That is the only option which is talking about fusion. This question. Question number 5. Deuterium and tritium are used as fuels in nuclear fusion reactions. That is true. There is no risk of meltdown in nuclear fusion reaction. That is also true. To date, there has been no net gain of energy in fusion reaction. That is not true. As of now, there has been energy gain. I just mentioned that. Lawrence Lab, National Ignition Facility. So 1 and 2 only. This was a question asked by UPSC, I think in 2020 or 2021. This is one of those questions. All the options should be analyzed carefully. Some use uranium, others use thorium. We haven't started as such thorium use at very large scale, right? So first, in any case, is not true. Some use imported uranium, others use domestic supply. I'm not very sure about that. Let's look at other options. Some are operated by foreign enterprises, others are operated by domestic enterprises. If there is foreign collaboration, there should be no doubt that all of our reactors are run by domestic enterprises only. 100% FDI and 100% allowing of nuclear reactor by foreign companies is not allowed in India. Yes, there are collaborations. There are some reactors which are built with the help of Russia, some reactors built with the help of US, but many reactors are indigenous. But one thing which is very common in all of those reactors, that only and only giving management and decision making power to foreign companies, ये permitted ही नहीं है, और ये permitted आने वाले time में भी नहीं होगा. FDI will be allowed, those things will be allowed, but ये जिस तरीके से statement है, ये बिल्कुल ही सही नहीं होगा. Some are state owned, others are privately owned. All of them are state owned. This is again one of the options, that all of them are state owned. All of our nuclear reactors are state owned. There is no private sector participation in any of the nuclear reactors. In coal-based thermal power plant, in some other plants, yes, there is private participation, but in nuclear power, there is no private participation. All of the reactors are state-owned. The option left is B, which makes sense. Why IAES safeguards? We adopted a policy of transparency to International Atomic Energy Agency, that some of our reactors, there was a fear. I told you that after 1999, when India announced to the world that we have an atomic weapon at our arsenal, then that led to a lot of economic sanctions on India. And India had to then prove that we are a responsible nuclear nation. It did a lot of things. We adopted no first strike policy. I talked about that how we will not attack a nation with nuclear weapon, but we will retaliate. Another thing which we did is that we allowed global observers belonging to IAEA, this is an agency of United Nations, UN ka part hai, that if you have a fear that India will be given uranium and India will start using that uranium for enriching to make a atomic bomb, then you come and look at what we are doing. So that is why we adopted this IAEA safeguard. And of course, we will not allow you to go to our own uranium reserve and what are we doing to that. But if the fear is that imported uranium will be used to make into nuclear weapons, then we adopt 100% transparency here. And you can come and check our facilities that what are we doing to that particular uranium. That is why B is the correct answer. This is one of the questions where we should analyze options and find the right answer. What about this question? बिल्कुल. और this is why this is not a very good question. ये UPSC की गलती है फिर. ये बहुत पुराना क्वेश्चन है वैसे, 2010-11 में कभी आया था. The function of heavy water in a nuclear reactor, A भी हो सकता है, C भी हो सकता है. If I have to choose between A and C, I will choose A, because heavy water is very good moderator. Water can be a very good coolant, but heavy water particularly is a very, very good moderator. So answer is A here, and UPSC also gave the answer, official answer key as A, but you are absolutely right, that answer can be C also. Not a very well-framed question, right? Let's complete this application in medicine part. I was talking about radiation. Sorry, क्या लिखा था हमने? Nuclear medicine. Nuclear medicine देखो क्या है? Go to all the topmost hospitals, go to AIMS, go to Max, go to Medanta. You'll find there is a particular place called nuclear medicine department. So nuclear medicine often is used for diagnosis, that what are you suffering from, to know about diseases. It can be cancer or even other diseases. How does that function? It includes various type of tests. One of the most famous one is called PET scan. So often what will happen here is that you will be injected often with a radioisotope. A radioisotope which emits gamma of very, very low level of radiation, because it cannot cause damage immediately to the human body. But as this gamma radiation, as this radioisotope now spreads throughout the body because of blood circulation, so patient will be asked, once the injection has been given, patient will be asked to wait for 1 hour or 2 hours, so that this radioisotope is not now the entire part of the body. And it will give off very low doses of gamma radiation. This low doses of gamma radiation, how does it interact with healthy cells versus how does it interact with tumorous cells, cancerous cells. It can be recorded on a computer screen. So understanding the interaction of that gamma with cells and tissues of your body allows doctors to know that if cancer is localized or if cancer has spread to many parts of the body. Right? I particularly, I do not have any background in medical science. I know it that because my mother had a cancer scare. Like, of course, nothing, one of the doctors said that she's suffering from stage 3 cancer. But then turns out that that was false, completely false, and that was a huge relief. But there I got to know a lot about how we have applications of nuclear technology in even diagnosis part. I knew about the treatment part, but the diagnosis part became much, much more clearer that how does it function, how does it exactly function. So the nuclear medicine department hai, that plays a very important role in diagnosis of various type of diseases, including cancer. आप लिख सकते हो? With help of radioisotopes, doctors can determine spread of a disease or to confirm a specific disease such as cancer, but not just specific to cancer, for other diseases also. And one more application I can talk about here is radiation sterilization. This is very similar to food irradiation. The purpose of food irradiation was to kill microbial organisms. Same purpose is here, that जो hospitals हैं and जो hospital labs हैं, they are hub of infection. So many dangerous bacteria and viruses. जो biomedical waste है, it's one of the most dangerous type of waste out there. So how to kill microbial organisms? One method can be chemical treatment, but use of lot of chemicals is polluting, right? Rather than using chemical treatment, we often use nuclear treatment. So a lot of surgical sutures, syringes, gloves, even medical devices, they're exposed to gamma radiation. And that gamma radiation kills all of the microbial organisms, bacteria, viruses, worms, everything. And that becomes free of those dangerous bacteria. So in fact, you'll find this, that lot of bandages आप market से खरीदोगे, there is a chance that वहाँ पे लिखा होगा कि this has been sterilized by radiation. And that is nothing but sterilization by nuclear radiation, so that it essentially kills all the microbial organisms and it is safe to use again. आप लिख सकते हो, use of gamma radiation, to sterilize syringes, gloves, medical devices, among others. There are a few questions here. If X-rays and gamma rays are very much harmful, then why their use for food processing? Will it not harm the nutritional benefit of the food? Not a lot. That nutritional benefit जो harm है, it is negligible. It will kill microbial organisms. अगर ये safe नहीं होता तो हम use नहीं करते इसको. So it is already used actually. In first strike policy, if enemy attacks in non-nuclear manner, can we respond with nuclear might? First strike, no first strike policy का मतलब ही यही है कि we have been attacked from a nuclear weapon and then we retaliate with a nuclear weapon. Just 5 more seconds. In next class, we will complete this topic in first half an hour. And the next topic, which will be a very small topic, I will complete in then and there in the next class itself, is nanotechnology.